In this video, we're talking normal distribution. Look, we talk about a lot of distributions here. We talked about binomial distribution. We talked about probability distribution. Those are those table distributions. And then we talked about uniform distribution. And now finally, our fourth installment, normal distribution. Whenever you hear distribution, I'd encourage you to focus on two parts. The first is identifying the situation and trying to figure out which distribution it fits into. And so it's very important when we hear distributions to understand what characteristics we're interested in. Once you know what distribution you're in, well, the second thing to worry about are tasks. What are the tasks that you may be asked to perform within that certain distribution? Each distribution has its benefits and those tasks that we can perform in them. So let's dive in and do a little bit of a warm-up here for the normal distribution. The normal distribution is a continuous distribution. It's for continuous random variables. And so let's see if we can list three different continuous variables. One example, again, whenever you hear continuous, you should be thinking things which are measured. Something like height is a good one. Something like temperature is another good one. And then maybe to make it more education related, we can say something like a grade, something that's measured. That's usually what we associate. So all these different variables, depending on what the data looks like, are good candidates for the normal distribution. To recap, the uniform distribution is very friendly, but it relies on this whole concept of things being equally likely and then everything being defined inside of some world. C and D were the characters we used. This one was like 2 to, let's say, 8.7, and that's the world that you're living in. Normal distribution isn't quite as limited. In fact, for the characteristics that make up a normal distribution, it's really hinged upon the center where your most observations and then what the spread is. But let me get to why it works out this way. What we'll find oftentimes with data is many people are quote unquote normal. There's a common center point where most data or most points are located. If I do a little zoom in here and look at this chart, this is a graph of the normal distribution. And we can see right over here, this is the center, the mean, and that's where most of your data located. Again, this is a frequency distribution. The frequency is centered around the mean. And it looks like as I go out on either end, either to the left, smaller than the mean, or to the right, larger than the mean, the frequency drops because, again, less common to be out there. This shape is very special. We have a name for it. I'll talk about it in a minute, but this is the characteristic or the shape that we look for the normal distribution. As a side note, as we continue, Excel is going to be used for normal distribution for two different tasks. And so watch out for those as we continue to practice using Excel. So like I said, two important things to focus on for distributions in general: identifying that distribution and also performing tasks. Let's talk about that first point of identifying the normal distribution. The normal distribution is ubiquitous. It's all over the place. In fact, if ever you hear the word normal distribution, think of common. It's the most standard distribution, although try not to use the word standard. It actually means something else. Let me slide down here while we talk. Here we go. So the normal distribution is used in psychology, yes, business, economics, yes, sciences, nursing is especially common for these distributions. You see, look, this is how most patients are behaving. And you have your extremes on other ends, and that's how you're going to identify, hey, this person's atypical and whatever their characteristics may be. And of course, here we are in a math class. Yeah, we're going to talk about normal distribution. That first task, if you remember, is identifying normal distribution. How do we fit a situation into normal distribution? Well, if you have a random variable, there's two characteristics that we're looking for in data in order to fit normal distribution. Kind of. There's technically three. Those two characteristics that make up a normal distribution are a mean and a standard deviation. A center, where's most of your data, and a spread, how wild is your data. If you have these two ingredients, you're close to normal distribution. And here's why. If you remember, for all of our distributions, including binomial distribution, we had two ingredients for binomial. I had n and p equaled n my number of trials and p my probability of success. And that's how we knew, hey, you're off to the races and you could perform probability, yes. You could also, for binomial distribution, find a mean and a standard deviation for binomial distribution. So doesn't that mean if you have a situation that's binomial, couldn't you then find the mean and the standard deviation, and then with these two, go into the normal distribution? Close, because the normal distribution needs something else. It needs to fit that proper shape. In fact, for binomial distribution, especially if you have a small p-value, like 0.05, unlikely, then your distribution is going to be skewed rightward. It's going to look like this. It's going to be skewed to the right, where the mean isn't necessarily going to be in the center. The mean might be somewhere over here, meaning that distribution, although just because it has a mean and a standard deviation, doesn't mean it fits normal. Nope. needs to be bell-shaped. Bell-shaped and technically symmetric. We'll get into it. We talked about, let me slide out of the way over here. We talked about the uniform distribution, how it had a PDF function for uniform distribution. It said f of x is equal to 1 over d minus c. This was the PDF for the uniform distribution. That was how we got the graph, the uniform constant function graph. For the normal distribution, the graph's a bit more complicated. Oh my goodness, much more complicated. Fortunately, we don't need this, but the PDF function is useful for graphing. And so if you see this funky bell shape, you're thinking, look, how did we get there? Well, here's a function on how we got there. 1 divided by the square root of 2 pi standard deviation, e, which is Euler's number. It's a very fancy constant, kind of like pi. And it's raised to the negative all the way up here. Here's the x value, my random variable, minus the mean quantity squared divided by 2 times the standard deviation. Again, complicated formula, but we should appreciate when we look at the graph and we see these pictures where it's coming from, and that's exactly the function that we're showing you here. A little recall, make sure we don't make a mistake in the future, that look, for probability, for normal distribution, and for uniform distribution, if you're ever interested in one specific value, the probability always going to be 0. And so it's something we can take for granted. If they're ever asking you, hey, look, what's the probability, for instance, that a height is 71 inches? Is impossible. What other characteristics make up the normal distribution? We talked about the mean, again, that's the center where most of your data is. And we talked about bell shape, that it makes that shape. But that shape is actually dependent on those two ingredients, not primarily the mean. The mean will just shift your graph from left to right, depending on where that mean is. But the standard deviation is what's going to affect the curve of your graph. In fact, a nice key frame to think about it, let me zoom in here so we can get a good picture. A way that we can think about the shape is with the standard deviation. Now look, if you have a small standard deviation, look at this yellow graph over here, that's the mean, 1200, and the standard deviation is 50. If you have a small standard deviation, well then you don't have much spread. Your spread is kind of narrow. You have a high peak, a narrow bar graph. If you look at this blue graph, again, the mean is moved over 900, so that's why it shifted the graph over. Look at that standard deviation, 120. Well, when I have a larger standard deviation, I had narrow before, and then over here, now for this blue one, it's quite a bit wider. And so I have a more shallow peak. You can even see this exaggerated in the red graph. The standard deviation is 220, and so look how flat that normal distribution is. The reason why we care about the shape is because it tells us the behavior of the data. If I have a very narrow standard deviation, small spread, I can look at my chart and I'm like, hey, look, most individuals are right around that mean. For the yellow, that's 1200, right? There's not much deviation. There's not much movement around that point. Most people are common there. But the wider that spread gets, the more I'm like, okay, look, this data is wild. It's all over the place. And that's exactly what the high peak or the low peak shows, the narrow and width of my chart. And so it's a nice thing that we can pay attention to. I can look at the graph and I can determine which data is wilder. There's a couple key characteristics of the normal distribution that we should know, and that is, look, 50% of the data is to the left and to the right of the mean. In fact, we had a very special name for the 50th percentile, or right smack dab in the middle. For this blue one, let me get out of the way here so we can see it a little better. For this blue graph, I can draw a line down the middle, that this is the mean. But also, I know that 50% of my data is to the left of that, and 50% of my data is to the right. We also had another name for this, and it was the median. And if you'll recall, whenever the median and the mean are equal, we called that data symmetric. And that's certainly what the normal distribution is. And so it's a nice thing that we can hold on to. 50% of the data is on the left and the right of the mean. If I can get out of here one more way. We're very interested in the spread and how wild my data is. If you remember from the empirical rule, we talked about that a while ago, it basically said you have these standard spreads that are going to contain so much data. 68%, 95%, and this last one is 99.7%. It said, look, if you have the mean plus or minus 1 standard deviation, you're going to contain 68% of your data. The mean plus or minus 2 standard deviations, 95%, and then this last one, plus or minus 3 standard deviations, are going to contain 99%. Why do we need to know this? If I look at my chart, again, we can see the chart in yellow that I drew. Let me zoom in, we can get a better view of this. That if I go plus or minus 3 standard deviations, in this case, it's from 1050 all the way to 1350, and that's going to contain, well, almost all of my data. In fact, 3 standard deviations, that's 99.7% of my data by probability. And so these are nice mile markers that we can use to say, hey, look, this is the spread. This is about as wild as my data looks. Much like for normal distribution, how we have those bounds that exist, It's kind of what we can perform here. We can produce these endpoints that say, look, these are the extremes. On the lowest end I can imagine is 1050, and on the highest is 1350. You can compare that with maybe the blue or the red, how wide that range is going to be. And so it's an important characteristic to think about whenever we hear normal distribution. Empirical rule should be in the back of our mind, because these two often go hand in hand. In fact, the one thing we said for empirical rule is your graph needs to be bell-shaped. And so it's a nice thing to hold on to, and certainly relates to the normal distribution. It's, again, one of the big characteristics. So I want to get comfortable reading and working with these charts. This example demonstrates us getting more familiar with them. Consider the histograms for each part and draw a bell-shaped curve over the histogram representing the normal distribution as like an approximation ideal. Then we're going to estimate what the center is or what the mean is. And then we'll look at filling in either a K or probability, depending on what they're asking, that satisfies the condition. We'll do an example here. For the first one, let's say we have exam scores for a statistics class, and here's the histogram that we're shown. To draw a bell-shaped graph, I can do so. Goes up and then back down again, where I can see the center point, or the mean, is right here. I'll write mean right here in the middle, and maybe we'll approximate that to be, let's go for 78. I like that. That's a good center. 78. If you said 79, 77, that's perfectly fine. We're just getting an idea of where the middle of this distribution would be. And then I want to talk about probability. Anytime you see this notation, you can read it as probability that x is less than 60 is equal to. We want to see if we can get a good guess on what that would be. Less than 60, that would be like smaller than or to the left of. And so if I want to draw this on the distribution, I can do so. Let me pick green here. Here's 60. And I want to be less than that. So I can shade this in. Boop, boop, boop. It should look like this. This is the probability that we're asking to find. We're thinking, look, what's the proportion or percentage of values that are less than 60? I'm thinking not very much. Again, some mile markers we have is I know that right down here in the middle, this whole thing represents 50% of my data. Ooh, that green's kind of hard to see. On the right side is also 50%. And so I give you a proportion. It should definitely be less than 50. In fact, if I had to estimate, I'd probably say it's much smaller. Maybe I'd give it something like 10%. I'll write 10% or 0.1 for the probability there. And again, we can draw a picture. We can get an idea of what this looks like without necessarily getting out into calculations, although we'll do that shortly. Let me slide all the way for this next one. So similar tasks we're being asked to perform. We should draw a bell shape. It should go up, hit the peak, and then go down. Something like this. Okay, it doesn't have to be perfect, but just something rough so we can look at what our shape looks like. And it looks like, okay, if I have to draw the middle, I'd say it's probably closer to 4. Probably somewhere around here. We'll go with 4. You could do something like 3.9. That might be a bit better. But that's what we'll average the center or the mean at, 4. And now we look at probability. So I want to find, again, probability that x is less than, or you can think of that as left, of some value, we're not sure, is equal to 0.8. Or you can think about that like 80% of my data. As an exercise, I could imagine drawing a line down here at 2 and crossing this data. That would really only be like maybe 20% of my data to the left. That's not going to work for us. I need to go more. You could even imagine dropping a line here at 4. And if I went to the left or less than, this represent 50% of my data. Because again, the mean is smack dab in the middle. But I want to go a little bit more than that, capture more data. In fact, maybe I can go all the way if I get out of the way here. I like 5.5. That's a nice number. Pretty close to, we can imagine, 80% of my data below here. And if you said 5.5, 5.6, if you even said something like 6, hey, that's perfectly fine. But we should all be roughly around the same area to represent 80% of my data. The main reason that we do this is to get a little bit more comfortable with the graphs, of course, but also when we think about these different distributions, normal is the one that we're talking about in this example. There's really 2 tasks that you'll be asked to perform. The first one is probability. Can you compute it? Certainly we can estimate it, as we've just shown, but we can compute it as well. The second task that we're asked is to, given probability, can you tell me what X value got you there? Oftentimes we call that percentiles. And so we'll see these 2 tasks in practice using more sophisticated means than estimation. Let's see. So the first task within that normal distribution is, of course, probability. can you calculate it? This is more similar to binomial distribution, but in a continuous sense. Let me show you what I mean. So whenever we have probability that x is less than or equal to some k value, let's say 3, x is less than or equal to 3, we can compute it using Excel. With this Excel function right here, it looks like normal dot distribution, much like if you remember before for binomial distribution, it was binom distribution and it had certain inputs. So similar function. In fact, this function needs 4 inputs, one of which, the last one, is always the exact same. It says first input I need is that k value, the value we're switching on. I then need the mean, I need the standard deviation, again, that's what defines the distribution. And then I need 1, or you can type in true. I've typed up for your convenience some examples here. Example 1, example 2, and example 3. We'll do these examples shortly, but it's important to kind of prime us and get ready that, look, if we're interested in less than or equal to 3 or less than 3, again, for continuous, they are the exact same thing. You should type equals normal.distribution, the k value you're interested in this case 3, whatever the mean and standard deviation are, and then 1. And so what's friendly about these distributions when we're computing them, the mean, the standard deviation, the 1, these things are always given to you in the example. But it's that first input k that we're interested in, that's what we're switching on. If we're doing greater than, we've seen this before, if you're doing greater than 5 or just greater than 5, if you're doing greater than, in this case, greater than or equal to, or just greater than, we're going to do 1 minus. Again, we can't do greater than directly. I have to do it in terms of less than. So I take 1, that's everything in the whole wide world as far as probability is concerned, and then I take out, or I remove normal distribution. This is 5, probability that x is less than or equal to 5. I take out that less than, and that'll give me that greater than. This is a term of complement. So when you see less than, go in directly, boom, you got it. If you see greater than, okay, we just have to do the 1 minus trick. Now the hard part is when these two things combine, when I have a between situation. All right, friendly enough, and let me swing it out of the way here so I'm not blocking the Excel function here. We have normal.distribution for the 5. Again, this is probability that x is less than or equal to 5, and then minus the 3, probability that x is less than or equal to 3. And this will get you exactly the same thing as between. Again, the whole beauty of normal distribution, much better than binomial in my opinion, is we don't have to worry about, okay, do I include or not include those endpoints? For these continuous distributions, it's always going to be include, because again, adding that probability, the probability that x is equal to 3, let's say, we don't even do the calculation. I can tell you it's 3 right away. On a little formula sheet, you see it right over here, probability that x is less than or equal to k is equal to, and you can see the function typed up for your convenience. We'll reference that. Again, this is the first task that you'll be asked to perform in the normal distribution probability. And we'll do some examples here in a minute. The second task that you may be asked to perform are percentiles, or it's the inverse operation. Instead of me asking you for probability, I'll give you probability, and you have to compute the x value that got you there. These percentiles, or if anything, it's like an opposite operation, or the math word we like to use is inverse. It's an inverse operation. And so normal.inverse is the function that we use. And it requires only 3 inputs. And that's first, the probability that we're interested in, the mean and the standard deviation. The reason it works this way is it's only interested, much like we do less than or equal to for probability, for normal distribution, for these percentiles, that's exactly what we're going to do. We're restricted to only doing percentiles. And so the 65%, I can show you a picture over here, is, hey, look, what k value will get you 65% on the left and 35% on the right? That's exactly what Excel will compute for you. So sometimes you'll be asked questions like, look, we want 35% on the right, which equates to 65 on the left. And so we might have to do a little bit of manipulation. You'll see some examples here shortly. Just like before, I typed up some examples so you can see what this looks like in practice. For instance, if we want the left probability of 90%, or you can think about that as a 90th percentile. In fact, we'd write it like this: probability that x is less than or equal to some value we're not sure is equal to 90%. And so in Excel, I can throw that right in, 0.9, type in the mean standard deviation, and boom, we'll get what that k value should be. On a picture, it would look like this, where this probability represents 90% and this probability represents 10%, and it'll compute that line in the sand. For this example, Excel might give you something like 69.4. These are exam scores. One thing to notice is sometimes this is asked in an opposite way. Maybe I want to know the probability of the right is 0.1. This is not a percentile, but we can convert it into one. Again, we say to the right, that's going to be greater than, and it's equal to 0.1. And so then we need to convert that 0.1 to think of 1 minus, and that's where we get a 90 percentile. And then we'll get the exact same result. And so keep that in mind. Sometimes we're asking to the right, to the left, and we always need to, when we're doing percentiles or this inverse operation, to the left. Just like before, you can see a little typed up what this will look like on, let's say, a formula sheet, where it'll say the probability that x is less than or equal to k is equal to p, or p is known, say maybe 0.9. Again, we're trying to find k. Then I can do so by writing k is equal to normal dot inverse. And then p is the value. Again, the one thing to make sure is we're always writing this as less than or probability to the left. And we can use this function lickety split. These are the two tasks that you'll be asked to perform, but the way we do them sometimes is a little tricky. So let me do some examples to clarify how to compute these various probabilities. Here's our example. Researchers studying anthropometry, which is the study of measurements, because that's more interesting than maybe anthropology, collected the height for 507 physically active individuals. The histogram shows the sampling distribution of the heights in centimeters. And so we can see our distribution down below. Again, you may argue that it's bimodal is the word that we often use. It has two large peaks, but maybe we can smudge those over and call it normal. In fact, we have a very friendly phrase here. Assume the heights are normally distributed, woohoo, very fancy, with a mean of 171 and a standard deviation of S. Again, those are the two ingredients that we're always looking for. In this, they're telling us outright, don't even worry about it. This is approximately normally distributed. Our first task that we're asked is, can we draw a bell-shaped curve on the histogram? No problem. We're going to go up. It's okay if we cut the graph a little bit. There's our mean, there's our center, and then it goes down afterwards. And it looks like, hey, relatively normally distributed. In fact, I can write over here, it looks like this is where the center is supposed to be, 171, and that's the mean. And then, of course, the spread divides it out as well. Now that we have the graph, let's actually get into computing some probability, and we'll use Excel here in just a minute. Find the probability of individuals who are less than 180 centimeters. Like before we start jumping in and computing probability, we should understand what the event that we're interested in. In this case, I already have this pre-typed for us. Probability of my random variable x, or individual, is less than 180. Now you'll recall for any of these distributions, in this case we're doing normal, we should be looking at how to compute probability. For this one, probability is always computed less than or equal to some value. That value we wrote as k. But again, very fancy. For normal distribution, less than or equal to, they're the exact same thing. So now that we fit our proper form, again, you can look at the formula, or we can jump right into Excel, which is what I'll do here. And so let me open up Excel so we can get started. Let me slide over here. There we go. So we're interested in less than or equal to. Let me type it over here. Probability that x is less than 180. Again, very fancy. Since we're on the normal distribution, I can go in here and I can write equals normal.distribution. And since we're fit that form properly, we're already in less than, I can simply type in the x value, or k for us, 180. And then I need the mean, which is in the actual example. It said it was 171. And then I need the standard deviation, again, in the example, 9.4. And for this cumulative, you can either type the word true, or maybe to keep things simple, I'll just write the number 1. And that'll give me the probability that I'm interested in. I can bold that number. And so let me write it inside of our box, mostly for posterity's sake. And then you can see, hey, look at that. We match our same probability that we computed before. Actually, pretty likely, it looks like 83% chance that somebody's going to be 180 centimeters or less. Pretty common indeed. Let's read that second one. It says, find the probability of individuals who are 190 centimeters or taller. And then let me write out the probability that we're interested in. All right, probability that x is greater than, because we're interested in people taller than 190 centimeters. Albeit this actually says who are 190 centimeters or taller, so technically it's greater than or equals to. Again, this might throw us for a loop, but fortunately we know how to compute greater than. It's with 1 minus our probability. And so let me pull into Excel here, translate over here to Excel, and we compute it. Again, this is what we did for part A. I'll jump down for part B. I have the probability that x is greater than or equal to 190. Again, we can't do probability directly, so instead what I'll write is let me write a tick mark, equals 1 minus probability that x is less than 190. And this will get us a probability. So again, whenever you see greater than, don't worry, just do 1 minus, and we're done. So I would type it as equals to 1 minus normal distribution. And then I need the x value we're interested in. In this case, it's 190. Mean, same as before, 171. Standard deviation, 9.4. And then lastly, cumulative, you betcha. Ooh, we're almost out of space here. Let me copy and paste it. So there we go, we have our probability. If I slide it out of the way, you can see what we typed in there. Again, anytime you see greater than, think 1 minus. And so mostly for posterity's sake, let me write exactly what we got into our little blank above. Ooh, barely fit it in there. But we have our probability here. It's basically 2%. I mean, how likely is it that somebody's 190 centimeters or taller? That's 6'4". Unlikely. It looks like 2% of our population are greater than 6'4", which is the same thing as 90 centimeters. In order to answer the next one, let's actually pull up PowerPoint to see if we can answer properly. Down over here it says, is a person who is 180 centimeters tall considered unusually tall for this group? Whenever we hear words like unusual, we should think of, well, we can quantify that, can't we? That's exactly what probability is all about. Make sure we explain our response. To do so, let me slide over here. So is a person that's that tall unusual? Well, we know a couple things. For instance, when I talk about unusual, we're thinking probability. Is it unlikely? I know the probability that somebody's shorter, less than or equal to 180 centimeters. That was from up above. It was about an 83% chance. And so if I want to know if 180 centimeters is unusually tall, well, then maybe I can ask the question, what's the probability that somebody is greater than or equal to 180 centimeters? That's considered tall. Well, fortunately, these two events are complements. I know the probability, it's 17%. And so to put this together, they're asking the question, look, is it unusual if you saw somebody this tall? Well, again, it depends on what you think of 17%. I can tell you that the probability of somebody being 180 centimeters or taller is about 17%. I don't think that's necessarily unusual, relatively so, speaking common. Just for our reference for us empirical folks, 180 centimeters is 5 feet 11 inches. I'd consider that relatively, even though it is on the taller end, again, 17% of our population, it's certainly not considered unusual or strange to find. It's almost a 1 in 5 chance. 1 in 5, which is 20%. Okay, so that's how we can kind of quantify or think about that. Yeah, fairly common, not terribly unusual. And so whenever you hear the word unusual, think of it, we can quantify. 17% chance, maybe not super common, but common enough that you would definitely run into it and not think it strange or unusual. Next part, I want to find the proportion of individuals who are shorter than 3 standard deviations below the mean. Proportion, much like unusual, associate that with they're asking you for probability. The tricky part is they don't outright tell you what height we're interested in. Instead, they're saying are shorter than, think of that as less than. We want to have 3 standard deviations below the mean. That means it's like I have the mean here, but I want to be below. So I'm going to take away 3 standard deviations. And this is the x value, the mean minus 3 standard deviations. Again, the minus comes from the word below. And so I can compute these. They gave me the mean up above is 171 minus 3 standard deviations. It's going to be 3 times 9.4. I cheated. I did it beforehand. If you multiply these numbers together, you should get 142.8. For your reference, that's looking at 4 feet 8 inches. But that's the x value we're interested in. And so now we can reread this maybe a bit more friendly. Find the proportion or probability of individuals who are shorter than or less than 142.8 centimeters. And so it's about taking that phrase, translating into something that's calculable, and then I can write it here. And individuals are shorter than, less than 142.8 centimeters. Fortunately for us, we're in that less than category. I can jump right into the formula and compute. Less than goes right into equals normal dot distribution. And we had those 4 inputs. The first value was always k or x. 142.8. I needed the mean, 171. I needed the standard deviation, 9.4. And then lastly, a 1 to round us off. And so they wanted the proportion. I can tell you the probability is 0.0013. If they want it in a proportion, or a percentage, I can move that decimal place over and it's 0.13%. I'm thinking this is considerably unlikely. Don't count on it. But again, this is shorter. If I want to quantify that, I have my little graph up above. I'll write it and then zoom in on it. 142, I mean, gosh, we're talking about very much a minority here. I just wrote it, so let me zoom in. We can see it. There's my 142, again, less than 150. And I want to find the probability that's going to be shorter than that. So that's on the left over here. Unlikely. In fact, there's not very many of them. In fact, it's 0.0013% chance that you'll run into somebody. That is highly, highly unusual. So we can compute these things with probability. It's often important as well that we can identify them from the graph, that we understand why these things are small probabilities. We are far from the mean. Here's our next example. Find the proportion or probability of individuals who are between 164.7 centimeters, or 5.5, and 177.4 centimeters, that's 5/10. Whatever here between, I can go right into my equation here. I'm looking at 164 is my small n, less than x, less than on the large end, 177.4. That literally x is between. As we saw with different distributions, whenever I'm computing probability, look for what we know. On the right side here, this is exactly what we're interested in. This is that less than. I wrote up the form for this on the previous slide, but I can go right into it here why it works out this way. On the right-hand side, this is the probability that x is less than 177.4. And we can go right into Excel and compute that, no problem. But the problem is this is too much probability because I'm not stopping at this 164. And so I need a minus because this is greater than, and x is greater than 164.7. And so I need to subtract, take out the probability that x is less than 164.7. Whatever you see minus, they take out, remove. And so now I have these two different probabilities to compute. I can do the first one. This is going to be normal dot distribution. And I have the k value first, 177.4, and the rest are rote. I have the mean, 171. I have the standard deviation, 9.4, and then always a 1 at the end. And it looks like that probability, let me write it over here, is 0.7520. But don't forget to compute that other probability. The probability that x is less than 164.7. It looks similar. In fact, let me speed it along here. Everything stays the same except for the first entry, 164.7. And then we have the same mean and standard deviation. And it looks like that probability is about 25%. So I'll write minus 0.2514. And if I subtract these two, making sure I'm not in the way here, you should get 0.5007, roughly 50%. But there are other tasks that we can perform. Yes, we can compute probability. Again, we did many examples, but also we can answer things like percentiles as well. We can do the inverse. That's what this example highlights. A college counselor is interested in estimating the average number of credit hours a student will take throughout their college career. The counselor randomly samples 100 graduates. The histogram shows the distribution of the average number of credit hours taken each semester. Assume that the average number of credit hours are normally distributed. Okay, there's a nice hint. We know what distribution we're following. And we have a sample mean of 13.7 and a standard deviation of 1.91. Very fancy, already computed for us. Our first task that we're asked to perform is just, hey, can you draw a bell-shaped curve, please? Again, here's my top. If it helps, we can draw that mean sitting over here at 13.7. And so that should be the middle of our bell-shaped graph. Again, not perfect, but certainly we can imagine grabbing the top of that bell and giving it a ring. That is our normal distribution. Here's what tasks I want to perform. Find the 25th percentile of credit hours taken. Again, 25th percentile, very friendly. That's asking for the probability that x is less than some number we're not sure is equal to 0.25. Then when I draw up my data, then I'm looking for a line in the sand that 25% of data is below that point and 75% of data is above that point. What is that value? Fortunately for us, this goes right into a normal distribution function where this is k equals question mark. And I can write it over here. This is formula. Again, once we have this chart, it should be friendly for us. Let me open up Excel so we can see an example worked out. Let me also slide over here as well. This is our work from before. If I scroll down a bit, there we go, clean slate. I want to find the 25th percentile. So I'll write over here, this is for part B, and it says 25th percentile. Very friendly for us. We're looking for that K value. This fits exactly with normal, not dot distribution, but inverse, where we need a probability. And again, this probability is always to the left. And so that's why it's important to either draw a number line picture, like we have up here, where I know exactly how much probability is to the left. In this case, it's 0.25. Or if you want to be fancy, you can write 25%. If you want to be a little less fancy, you can write 25 divided by 100. I'm getting sidetracked. 0.25 is the probability that we're interested in. Then I need the mean, which we had in the example, 13.7. I need a standard deviation, 1.91. And we have it. These are all the inputs we need to find the 25th percentile. Let me bullet 4 decimals, maybe a bit too much. Maybe we want to round that to 2 decimals. And so I can round that to 12.41. And that's exactly our value we're interested in. Notice in this case, this is not a probability. This isn't point something. Instead, this represents credit hours that a student takes. So we're thinking, look, there's actually 75% of students take more than 12.4 credit hours, at least at this particular college. That's what we can find percentiles, very friendly to compute. But also what we're interested in is maybe finding 2 lines, much like we did in the previous example. Find the 2 credit hours which constitute the middle 80% of my credit hours taken. I drew a little chart here. Hopefully it helps us understand what we're interested in. I want to find the middle 80%. And so the mean splits things down perfectly in the middle. And then I have 2 scores that I want to compute. How do we compute these? I need percentiles. If we can understand these scores in percentiles, all right, P sub blank and P sub blank. Well, this question's over in a moment because once I have percentiles, we can use norm.inverse. Let me write a line dividing this 80 in half. I'm going to write it right on the mean. The main reason I want to do that is because I know that 50% of data is to the left of the mean. Let me write it outside here. 50% is to the left. And also 50% is to the right of the mean. So if I have 50% over here, crossing over to the left, and I know 40% is trapped inside, I can divide 80 in half, you'll get that 40%. Then I'm interested in how much probability is to the left of that particular score. You can do a little bit of subtraction here. 50 minus 40, that'll mean 10% of my data is less than that particular score. For the second value, for the second score, again, I had another 40% over here. You can just count the probability. It's 40 plus 10. That means my 2 percentiles are, my larger one would be P sub 90%, and my smaller one would be P sub 10. Whenever you're doing these inverse, or they want to know what credit score, always try to think of it in terms of percentiles, because once you get in percentiles, well, then you can compute the probability. So now if I go over to Excel, I have 2 functions to compute. I have P sub 90 for the 90th percentile, all right, equals norm.inverse. I can highlight and hit tab, or you can just click it. That should be 0.9 for the probability that we're interested in. The mean is 13.7. The standard deviation is 1.91. I close it off, and that'll give me my 90th percentile. That means only 10% of students are taking more than 16.15 credit hours. The next percentile is the 10th percentile. That's the smaller score amongst these 2, equals normal.inverse. I can know my probability is 0.1. Mean is 13.7. Standard deviation is 1.91. And I have my 10th percentile. My top performers, the 90th percentile, means, again, there's only 10% of students who are scoring or taking more than 16 credit hours. Meanwhile, on the low end, it looks like there are only 10% of students who are taking less than 11.2 credit hours. And so this is on my middle 80, what most students are doing for sure. Let me fill this in for posterity's sake. And these are my 2 values that we're interested in. And so let me pull up PowerPoint so we can actually talk about these particular values. And so again, there's really 2 big tasks that you're asked to perform. It's probability, we can do that, and percentiles. And percentiles is really what this example highlights. But there's actually a lot more that we can do with probability and percentiles, and that's what this example helps highlight. A little blast from the past here. I want to find the upper fence used in identifying outliers, given that we have our quartiles here. Again, anytime you hear fences, I think there's a formula for that, and there is. All right, UF, for upper fence was equal to Q3 minus 1.5 times a fancy number called the IQR. If you're wondering what the IQR was, I can write it over here, that the IQR is going to be Q3 minus Q1. And so let's compute that directly, and then we'll go to the upper fence. Q3, it says, is 15, very nice, minus 12.4 for Q1. It looks like our inner quartile range is going to be 2.6. I can then bring that up and plug it into my upper fence. When you're like this, I can write equals. For Q3, that was 15 minus 1.5 times the IQR, which we just computed was 2.6. I bring this down over here. Upper fence is equal to 18.85. And this represents, again, credit hours that are kind of on the upper extreme. If you'll remember, we used fences to identify atypical or outlier values. In fact, if I look at my chart and my graph over here, 18.85, my upper fence, is way out on the right side. This is my practical data. When I translated it into normal, again, it wasn't exact. And so I can find probability, again, even though my graph doesn't show any events outside. Find the probability that a student averages more than the upper fence. So if I wrote that, that would be probability that X is greater than the upper fence. We know what the upper fence is. It's the probability that X is greater than that 18.85 number. Let me go right into my formula. Again, keep in mind, whenever you have greater than, you should be thinking, I need to do 1 minus. And I can jump right into Excel, like right here, equals 1 minus normal dot distribution. And I'm looking for those 4 different inputs. The first one is the K value, 18.85. I need the mean, 13.7. The standard deviation, which I need to move out of the way for, 1.91. And lastly, a 1. And we'll get a probability over here. Very unlikely. In fact, if I had to write that, it'd be 0.0035. If you wanted to think about it in terms of percentages, that's 0.35%. Unlikely, don't count on it, which should make sense for fences, that it's very unlikely for this to occur, because that's what we call outliers or atypicals when they're outside. So the probability, not likely. Let's see if we combine the upper fence and the lower fence and see if we can answer a particular question. Let me slide over here to answer it. The lower fence is 8.54, something that was done for us, let's say. And the probability that we're to the left, that we're outside of the lower fence, is, interesting, the exact same probability, 0.0035. What is the probability that a student averages an atypical number of credit hours according to the lower and upper fences? So I have 2 values. I want to know probability that we're outside the upper fence, so at UF, and lower fence. Fortunately, I know the probability that we're outside the upper fence. That was my 0.0035. And I also know the probability that we're outside the lower fence, that's what's given to us, is the same, 0.0035. Again, less than the lower fence, greater than the upper fence. This is what's going to give you an atypical and outlier. So if I want to know outside both of those, I can simply add those together, and I should get 0.007. This is the probability that we're outside, that we identify an outlier or atypical value. If I want to put that in percentage, that's 0.7%. And that's our threshold, at least for fences, for what we consider to be unlikely. And the benefit or the beauty is in the normal distribution, this actually looks relatively similar for whatever your data is. Because again, these fences are based on quartiles. Quartiles are based on percentiles, or based on lines in the sand from your data. And so depending how spread apart your data is, that'll affect what we consider to be atypical. And the formula for the fences will compute that for us. But this is a mathematical point to say these are atypical, and we can compute those with fences. To show you really quickly here, there are some additional examples I have pre-typed up for you if you'd like to look at them and try them on your own. Make sure you get the same answers. I have this example. You can read it on your own if you'd like. And also the example afterwards, highlighting those 2 tasks that you may be asked to perform. And so again, these are just some additional examples you can work through that I want to type the solutions out for you. So let me wrap with this. Again, there are 2 big tasks with any distribution. You should know what characteristics define it. For this example, for normal distribution, look, do you have a mean, do you have a standard deviation? And of course, are you bell-shaped? The question primarily, especially in this one that we just saw, it'll say something like, hey, look, this data is normally distributed. Once you have your distribution identified, you should be able to sit back, relax, because there are certain tasks that you may be asked to perform. For a normal distribution, right now at least, probability and percentiles are tasks that were asked. But those tasks look different. Certainly you can see in this example, we do probability, but we do it maybe in a different way. So it's important that you understand those two tasks and also the myriad of ways that they could be asked to perform. This is true for all distributions. This example is for normal distribution. If you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.